morning, students. I am Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. Today, we are going to continue our discussion on exponential distribution. In the previous lectures, we have understood what is an exponential distribution and we have solved some problems on exponential distribution and we derived the mean variance of exponential distribution. Apart from that, we also discussed the memoryless property of exponential distribution and have seen some applications of memoryless distribution, memoryless property. And today we are going to derive the MGF, that is the moment generating function of exponential distribution, and the CGF, the cumulative generating function of exponential distribution, and we are going to obtain the mean, variance, and the skewness kurtosis. And apart from that, we are also going to see some real-time applications of exponential distribution. Let us start our discussion. So let us recap the definition of the density function of exponential distribution. As we discussed earlier, it is nothing but a time-oriented probability calculation function, that is f of x is equal to lambda into e power minus lambda x, where x is the time and time is always non-negative. We have x greater than 0. And lambda is called the parameter of the exponential distribution. And we also observed that the mean of the exponential distribution is 1 by lambda and the variance is 1 by lambda square. So, also we have derived the distributive function of the exponential distribution in the following way. That is, we started with the definition capital F of x is equal to p x less than or equal to x, which is nothing but integral x to infinity small f of x dx, that is the sum of all probabilities starting from x to the infinity. And we have substituted the density function, that is lambda into e power minus lambda x dx, and after integration we arrived at the answer 1 minus e power lambda x. So we also found that the distributive function of the exponential distribution is 1 minus e power minus lambda x. So that is what summarized here. Okay, that is as time is always positive and it cannot be a negative, so it is 0, and on the positive x-axis it will be like this. Okay, now you can see the various projections or the progressions of exponential distribution at various lambda values. See, let us recap that the density function of the exponential distribution is f of x is equal to lambda into e power minus lambda x. If we replace this here, if we substitute lambda is equal to 0.5, then it becomes f of x is equal to 0.5 times e power minus 0.5x. This is one of the exponential distributions, and the curve will be represented with the red colored curve, that is this one. Okay, so this is the graph. This is the graph of the exponential distribution with the lambda is equal to 0.5. Because it is negative exponential, it shows always the declining trend. That means it always falls down time to time in the regular intervals of time. It decreases as the x goes along. Okay, and when lambda is equal to 1, the f of x is 1 into e power minus 1x, that is e power minus x, which is represented here, which is represented with the black colored the function, that is this is the function. This is the corresponding exponential distribution. And at lambda is equal to 2, it is represented with the green color. And at lambda is equal to 4, the distribution has been represented with the blue color, dark blue color. So what did we observe? As lambda goes on increasing, towards the left axis, y-axis, the curve becomes steeper, and towards the x-axis, the curve becomes very nearer to the x-axis. So we could understand the trend. That means always the exponential function, the exponential distribution function always declines, and as lambda goes on increasing, towards the y-axis, it becomes the stiffer. That means first it is like this, then it becomes like this, then it becomes like this. And towards x-axis, first it is little deviated from x-axis, then it is inclined towards x-axis more, and then it is more inclined like that. It is moving. Okay, so that is what we have observed. Now, here we are going to derive the MGF. That is, we are going to derive the MGF of exponential distribution, which is an important result to calculate the skewness, the kurtosis, and the mean and variance. Let us see how we are going to derive the MGF. So let us start with the definition of an MGF, that is mx of t, that is expectation of e power t capital X, where x is the random variable. Because here our x follows exponential distribution under the parameter lambda, we can write it as integral x into integral e power tx into f of x dx. Okay, you know the definition of expectation, integral e power tx into f of x under the limit 0 to infinity. Why we have taken the limit 0 to infinity? Because we already assumed that under exponential distribution, x is always greater than or equal to 0, that, and hence we have the limit 0 to infinity. Now, let us substitute the density function of the exponential distribution, that is e power tx into lambda into e power minus lambda x. We have substituted the density function. Now, as bases are equal, powers start to be added. That is why we will get integral 0 to infinity e power tx minus lambda x dx, which will be equal to lambda into integral 0 to infinity e power minus x into lambda minus t dx. Because I have taken the minus x common, automatically it becomes e power minus of x times lambda minus t. Now, you know integral e power ax, that is e power ax by a. By treating this as a, we get integral ax, that is integral e power ax by a. Okay, integral e power ax by a under the limits 0 to infinity. Now, let us substitute the upper limit infinity and the lower limit 0 in the place of x. Then what do we observe? That is e power minus infinity minus e power 0 by minus of lambda minus t. So, as we know that e power minus infinity is always 0 and e power 0 is always 1. Okay, we know that e power minus infinity is always 0 and e power 0 is always 1, and e power plus infinity is always becomes the infinity. So, as per the behavior of exponential at various values, e power minus infinity is 0 and e power 0 is 1, we got lambda into 0 minus 1 by minus of lambda minus t, and hence we got lambda by lambda minus t. That means we are successful in deriving the moment generating function of exponential distribution, and which is nothing but lambda by lambda minus t. Okay, so let us summarize this in a single line. The summary is the moment generating function of the exponential distribution is lambda by lambda minus t, where x follows exponential distribution with the lambda and the variable t. Okay, so we got the moment generating function. Now we are going to derive the cumulant generating function. So our next thing is deriving the cumulant generating function. So to derive the cumulant generating function, first we will take the moment generating function, that is mx of t, that is equal to lambda by lambda minus t. Now let us apply log on both sides. Apply logarithm on both sides. Why we are applying logarithm? Because we know that the cumulant generating function is nothing but logarithm of moment generating function. That is kxt is always the log of mxt as per the definition. So we have already derived the moment generating function, and to derive the cumulant generating function kxt we are applying log on those. That means log of mx of t is equal to log of lambda by lambda minus t. Okay, now uh, log of mx of t is abbreviated as k suffix x of t, which is cumulant generating function. And here, log m by n. Let us recap the formula log m by n, which is nothing but log m minus log n. So by using that formula, we can write it as log lambda minus log of lambda minus t. So what did we get? Kx of t is equal to log of lambda minus log of, by taking the lambda common, we get 1 minus t by lambda. So this is the thing where we arrived at. Now let us recap one more formula. Log of mn. What is log of mn? Log m plus log n. So here when we see this, it is like log m into n. Log mn, that is, we have minus of log m minus log n. Okay, and hence we get log of 1 minus t by lambda. So what did we get? We have obtained the cumulant generating function of the exponential distribution, that is kx of t, that is log of 1 minus t by lambda. So after summarizing these things, we got the moment generating function mx of t as lambda by lambda minus t, and the cumulant generating function kx of t as log of 1 minus t by lambda. Now we are going to derive the cumulants. We are going to derive the cumulants and skewness. We are going to measure the skewness and kurtosis of exponential distribution. So next we are going to derive uh, what is the cumulant, what are the cumulants, and what is the skewness of exponential distribution, what is the kurtosis of the exponential distribution. Okay, let us try to find them. So first let us consider the cumulant generating function, that is kx of t log of 1 minus t by lambda. Now let us recap a formula, that is logarithmic expansion, which we come across in our intermediate course, that is log of 1 minus x will be equal to minus x squared by 2 minus x cubed by 3. Of course here we get minus, so this is minus x cubed by 3 minus x power 4 by 4, and so on. So by using this formula, we can write log of 1 minus t by lambda with minus, okay, that is minus of minus t by lambda minus t square by lambda square into 2 minus t cube by lambda cube into 3 minus t power 4 by 4 into lambda power 4, and so on. Okay, and by multiplying with the minus, we get t by lambda plus t square by 2 lambda square plus t cube by 3 lambda cube plus t power 4 by 4 lambda power 4. Okay, and also we can write it as t by lambda into 1 factorial plus t square by lambda square into 2 factorial plus 2t cube by lambda cube into 3 factorial plus t power 4 by, that is 6t power 4 by lambda power 4 into 4 factorial, and so on. So finally, we have expanded the cumulant generating function. Here we have written the cumulant generating function of exponential distribution, and we have expanded it by using the logarithmic expansion. Okay, and we obtained an infinite degree polynomial in terms of t. Okay, with quotients. T power 1 has a quotient, t square has a quotient, t cube. Okay, like that we obtained a polynomial. Okay, now as we know, uh, the k1 for the first cumulant is the quotient of t power 1 by 1 factorial. Here, if you observe t power 1 by 1 factorial, the quotient is 1 by lambda. And the tk2, the second cumulant, is the quotient of t square by 2 factorial, that is 1 by lambda square. And k3 is the quotient of t cube by 3 factorial, that is 2 by lambda cube. And k4 is the fourth cumulant, that is the quotient of t power 4 by 4 factorial, that is 6 by lambda power 4. That means we have successfully obtained the first four cumulants, that is 1 by lambda, 1 by lambda square, 2 by lambda cube, 6 by lambda 4. In the same way, we can write the remaining cumulants, but we don't need them for the calculation of skewness and kurtosis. We need only first four cumulants. That is why we are confining to only first four cumulants, that is K1, K2, K3 and K4. Okay, now we are going to calculate the skewness and kurtosis based on the cumulants. Let us write what is our first cumulant. Our first cumulant is 1 by lambda. As we know the relationship between the cumulants and the moments, K1 is the mean. Okay. And what is K2? K2 we obtained as 1 by lambda square, which is nothing but variance, of course, which is equals to the second central moment. So second cumulant is always equal to the second central moment, which we have seen in the last class. So K2 is equal to mu2. And K3 is equal to mu3, which is nothing but 2 by lambda cube. Just now we derived K3 as 2 by lambda cube. What we know that always the third cumulant is equal to the third central moment, and always the second cumulant is equal to the second central moment. Okay, and also we know that the fourth cumulant is nothing but mu, or you can write K4 plus K2 square, which is nothing but mu4 plus and mu4 plus, let me rewrite it. K4 is equal to mu4 plus mu2 square. So it becomes K4 is equal to mu4 plus K2 square. Implies we get mu4 is equal to K4 minus K2 square, where K4 is just now we obtained is 6 by lambda power 4 minus K2. K2 is nothing but 1 by lambda square, that is 1 by lambda square whole square. That is we get 6 minus 1. Okay, let us recap just, yes, here. So we obtain 5 by lambda power 4. That is what mu4. So mu4 is 5 by lambda power 4. Okay, now we are going to calculate the mean we obtain 1 by lambda, and variance we obtain 1 by lambda square, and we have calculated mu3, that is 2 by lambda cube, and mu4 we got 5 by lambda power 4. Now we are going to calculate the Pearson's measure of skewness. What is the Pearson's measure of skewness? Let us recap. It is nothing but B1, that is mu3 square by mu2 cube. What is mu3? Mu3 is 2 by lambda, so 2 by lambda cube whole square. And what is mu2? Mu2 is 1 by lambda square, that is 1 by lambda square whole power 3. So it becomes 2 by lambda power 6, 4 by lambda power 6 and 1 by lambda power 6. That means it is 4. So what did we obtain? We obtained beta 1 is equal 4 and that is greater than 0. So what do we say when beta 1 is positive? We say that when beta 1 is positive, we say that it is positively skewed distribution. Positively skewed distribution. Okay. Now let us try to calculate the kurtosis. For kurtosis, let us consider the Pearson's measure of kurtosis, that is beta 2, that is mu 4 by mu 2 square. We are going to derive the kurtosis, which is beta 2 is equal to mu 4 by mu 2 square, where mu 4 is mu 4 we obtained 5 by lambda power 4 by what is mu 2? Mu 2 we obtained 1 by lambda square whole power square, that is 5 by 1, and hence this is 5. Here we have seen that beta 2 is greater than 3, and hence we conclude that the exponential distribution is leptokurtic. Okay, so so uh, in this derivation we have obtained the following things. First, we have derived the moment generating function mxt as lambda by lambda minus t, and the cumulant generating function kx of t as log of 1 minus t by lambda with a minus, and we have obtained the mean as k1, that is 1 by lambda, and variance, that is k2, that is 1 by lambda square, and we have obtained k3 is equal to mu 3, okay, that is equal to 2 by lambda cube, and we obtained k4, and we have derived that the skewness is 4, which is positively skewed, and the kurtosis, which is 5, that is leptokurtic. So in this way, we have observed the geometrical properties of exponential distribution and its MGF, CGF, and its mean, and its variance, and its skewness, and the calculation of kurtosis. Now, let us see some real-time applications of exponential distribution. Here, we are going to see a problem which tells that suppose that the longevity of a light bulb is exponentially distributed with the mean of lifetime 8 years. If a bulb has already lasted 12 years, find the probability that it will last a total of over 19 years. That means we have purchased a light bulb. Okay, we have imported it from USA, and we are guaranteed that the lifetime of these bulbs is on an average 8 years. That means these bulbs will work for up to 8 years on an average. Okay, and we know that the lifetime of these bulbs are exponentially distributed. Okay, and if we bought a bulb of this kind from the company and we already spent 12 years, and 12 years it has worked successfully, the bulb went 12 years successfully, and assuming the condition that the bulb has worked 12 years successfully, what is the probability that it will work more than 19 years? It will work more than 19 years. This is the question. More than 19 years. Okay. Now, let us try to find the probability by using the exponential distribution. So, first let us read the question. It is given that the lifetime of the bulbs are exponentially distributed and the mean lifetime is 8 years. That means mean lifetime is 8 years and it is exponential distribution. The mean is 1 by lambda. So 1 by lambda is equal to 8 and lambda is equal to 1 by 8. Okay, so now let us come to the question. First let us consider the statement. If a bulb has already lasted 12 years, find the probability that it will last a total of over 19 years. That means it is a conditional statement. It has two parts. In the first statement, a condition is given, and in the second statement, we are asked to find a probability by obeying this condition. By obeying the condition that the bulb has already lasted 12 years, we have to find the probability that it will last more than 19 years. Okay, so when we see a conditional statement, we apply the conditional probability, that is A given B. That is the probability of happening A obeying the condition B. That is the probability of happening of an event A bearing the condition B. Okay. So for this we have a formula P of A intersection B by P of B. By using that formula, we can write this as probability of the bulb lasting more than 19 years, because this is the probability we have to find. What is the probability that the bulb will last more than 19 years, given that already more than 12 years completed. Okay, so this statement has rewritten as more than, what is the probability that the bulb will last more than 19 years, assuming that it is already last more than 12 years. That means you can mathematicalize with the terminology x greater than 19 given x greater than 12. And we know by using the memoryless property, that is p of x greater than x plus y, given probability of given x greater than x will be equal to probability of y greater than y. So with this rule, this probability will be equal to p of 19 minus 12, that is x greater than 19 minus 12, that is p of x greater than 7. So to find the given probability, it would be enough to calculate this probability, that is probability of the light bulb having more than 7 years. Okay, now let's try to calculate this. So p of x greater than 7 can be written as 1 minus p of x less than or equal to 7. As we know that the complementary probability p of a complement is 1 minus probability of a. Now, according to the distributive function of exponential distribution, it is equal to capital F of 7, because capital F of small x is p of x less than or equal to x. By using this formula, p of x less than or equal to 7 will be 1 minus capital F of 7. That is equal to 1 minus e power minus lambda into 7. Because we know that the capital F of x by definition is 1 minus e power minus lambda x. So we arrive at this step, that is e power minus lambda into 7. But we already know that lambda is 1 by 8. So this is e power minus 7 by 8. And by using the calculator, we calculate e power minus 7 by 8. That is shift ln minus 7 by 8. As per the calculator, we have to use the button shift and followed by the button ln, the natural logarithm. And if we calculate this in this way, we arrive at 0.49 something, that is around 49% of chance. Okay, so in this way, we can calculate a time-oriented probability by using exponential distribution. Let us see a few more real-time applications of exponential distribution. So here, just we are summarizing thing. Of course, I told you 49, but it's actually 42%. Same problem has been explained by using the slides here as exponential distribution, and the mean lifetime is 1 by lambda is 8. That is what he's given. So lambda is equal to 1 by 8. And the f of x, that is f of x is 1 minus e power minus lambda x. That is what here. And they have used the memoryless property, which I have explained. And finally, we got 42% of chance that the bulb will last more 7 years. Already assuming that it has completed 12 years, and to cross 19 years, there is a chance of 42%. Okay. Now, here we are going to see one more problem or real-time application of exponential distribution under memoryless property. At the time a postal clerk spends with his customer has an exponential distribution with a mean of 4 minutes. That means mean of exponential distribution is 1 by lambda, that is 4 minutes. So lambda is equal to 1 by 4. Now, according to the question, suppose the customer has already spent 4 minutes with the postal clerk. Suppose you are going to send a speed post to the post office, and already the clerk has spent 4 minutes on your work, but still your work is not completed. So what is the probability that you have to wait at least 3 more additional minutes to complete the work in the post office? So according to the question, the probability of spending 3 more minutes. Already you spent 4 minutes. 3 more minutes means what is the probability that you have to spend more than 7 minutes, given that you have already completed 4 minutes. That is excluded. So this is the conditional, because this is a conditional statement. We have to write it as what is the probability that you have to spend more than 7 minutes, assuming that already 4 minutes are over. Okay. So according to the memoryless property, this conditional probability will be equal to the regular probability with the difference, that is P of x greater than 7 minus 4. P of x greater than 7 minus 4, that is P of x greater than 3. P of x greater than 3. So we have to find P of x greater than 3. Now to find P of x greater than 3, we use the formula 1 minus P of x less than or equal to 3. That is equal to 1 minus capital F of 3. That is 1 minus e power minus lambda into 3. That is e power minus lambda into 3. But according to the question, we have lambda is equal to 1 by 4. That is equal to e power minus 3 by 4. It will be approximately equal to 0.45 or like that. So there is a 45% chance that you have to wait at least 3 minutes more to complete your work in the post office. Okay, so now I'm going to quote some real-time applications where we will find exponential distribution. That means there are some real-time applications where we'll apply exponential distribution to assess some important probabilities, with the help of which we'll take some practical decisions to overcome the practical difficulties. Let us see some kinds of real-time applications of exponential distribution. The first application, the first and very important application of exponential distribution is predicting the time when an earthquake might occur. That means we can, basing on the previous statistics, there will be some earthquake prone areas like Japan. If you take the example of Japan, it's a quite frequently earthquake prone country. There are certain parts of Japan which quite oftenly come across earthquakes. Okay, so basing on the statistics, previous statistics, we can expect the next probabilistic time of next earthquake. That means in how many months there might be an earthquake, so that we could take some precautionary measures. The government or the governing system can take some pre precautious. It can become precautious and it can take some precautionary measures. Let us see the example. The exponential distribution is prominently used by the seismologists. You know, seismology is the study of earthquakes. So it is prominently used by seismologists and earthquake scientists to predict the approximate time when the earthquake is likely to occur in a particular locality. That means with the help of exponential distribution, you can predict the next interval of time at which the next earthquake is going to happen. That means after a few days or few months, after 1 month or after 10 days, what is the likely time within which the earthquake is going to happen, and so that you can plan, you can take precautionary measures to protect the properties and the uh, lives of the people and the lives of the animals, etc., which are living in their surroundings. And for this purpose, the history of the earthquakes and the other natural calamities occurring in a particular locality is recorded and monitored. We'll take the statistical records of the previous earthquakes occurred in that area and the level of earthquakes on the Richter scale. We'll take all the statistics. Okay, and this data acts as the information and is fed to the exponential distribution. And now you will plot the data on a graph and you will approximate those earthquake times. That means you will take a graph and you'll plot the times in the previous times where earthquakes are occurred, like 1900, 1920, like that. You will plot the data and you will approximate that data with an exponential distribution. Okay, that means if on the 1900 we have an earthquake in Japan, and in 1910 we have an earthquake in Japan. In 1915 we have an earthquake in Japan. Okay, then we plot the points like this, and we'll try to approximate them with an exponential distribution. Okay, and this data acts as the information, and it is fed to the exponential distributive function. The output gives an approximate time when the earthquake might occur. Then we will we'll with the help of this approximated exponential distribution, we'll try to predict the next earthquake possible time. Okay, this helps the environmental engineers and disaster management officials draft essential measures to avoid the loss of lives to minimize the property destruction. So that by taking the precautionary and adventure measures, we can save the lives of the human beings as well as the living beings, and also we can save the property. Okay, so this is a very important application of exponential distribution in the earthquake predictions. And exponential distribution finds its prime application in calculating the reliability of electronic gadgets. See lifespan of electronic gadgets. In assessing the lifespan of electronic gadgets, that means how long a laptop will last, or how long a mobile will last, or how long an electronic component will last. These kinds of calculations, because these are all time oriented calculations, these can be assessed with the help of exponential distribution, and hence we can take proper planning and proper prior care to protect our electronic gadgets. Okay, so exponential distribution finds its prime application calculating the reliability of electronic gadgets such as laptop, battery, processor, mobile phone, etc. It helps the engineers and manufacturers to know an approximate time of which the product will get ruptured. That means with the help of exponential, as I explained in the previous problems, we can assess how long a computer component will last. What is the probability that it will last more than 5 years? Okay. What is the probability that it will last more than 10 years? What is the probability that a computer component will last between 9 to 11 years? Like that, we can calculate the probabilities. And basing on the probability, suppose if this probability is 90%, then we can assure that, okay, this computer component is going to have a life more than 5 years. So we can buy. And if the probability more than 10 years is 85%, that means it has a good probability of having more than life of 10 years. So we can definitely prefer that gadget. Okay. And if the probability that it will last more than or less than 9 years is 85%, that means we have to think whether to buy the gadget or not, because it is has a very high probability that it will go off within 10 years, 85% chance that it will go off within 10 years. So we have to rethink then before buying the gadget. Like that, we can calculate, we can assess, we can make decisions to buy those electronic gadgets or not. Okay, basing on the lifetime calculation probabilities. And in the similar way, while establishing a new shop, a person tends to consider a variety of factors that may affect. One of such key factors is the number of customers arriving at the shop in the first week. That means what is the intervals of time that customers arrive into the shop. So is there any necessity to start a new billing counter to be incorporated? Because if there is a more heavy rush, we have to start a new billing counter in our shop. Okay, it's like that we can basing on the probabilities of arriving of customers and the inter-arrival times, inter-departure times, we can plan of our improving our business, starting of new counters or enhancing our business like that. Okay, and purchasing flight tickets also. We'll calculate what is the probability of completing 50% of flight tickets booked within 20 days. We'll calculate the probability of completion of 50% bookings. Okay, we'll estimate the number of days that is going to be taken, number of weeks within which 50% of the bookings will be completed. Or we can assess the number of weeks within which 90% of the bookings will be completed. So these kinds of probabilities can be calculated by using the exponential distribution. Okay, most travelers tend to buy their flight tickets a few days prior, because in flight journey it will be very difficult to buy the tickets at just before the taking of the flight. So we will plan to buy the tickets in very advance, few at least few days before the planned time. Assuming that the maximum customers tend to buy their tickets 15 days before they execute a journey, the probability that a person will book a ticket 10 days prior to the actual date of commencing the journey can be calculated with the help of exponential distribution. That is, we can calculate the probability of that a customer will book his ticket in prior 15 days to the date of journey, okay, commencing the date of journey, assuming that generally 15 days the customers will book the tickets in your airlines. Okay, assuming that this condition, we can calculate the probability that he will book 10 days before his actual journey. Okay, these kinds of probabilities can be estimated with the help of exponential distribution. This helps the flight managers to maintain appropriate customer to occupancy ratio in advance, so that they can plan how many seats are to be arranged in the airlines. Depending on the advance reservation, they can plan how many seats are to be arranged, how much distance they are to be placed, how comfort they can make their travelers like that. Okay, it also helps the transport marketing managers draft appropriate deals and offers to attract potential customers. And if, to increase the rate of advance bookings, they can offer discounts and they can attract more number of customers in the festive seasons like that. Okay. Similarly, average time a call center employee spends with the customer. How long a call center employee is spending on his customer, and how long they are totally spending on an average, how time they are busy with their customers. These kinds of probabilities can also be calculated with the help of exponential distribution. If the average time that a call center executive takes to complete um, is known to be 20 minutes, then the probability that the executive will handle 8 customers per hour can be estimated with the help of exponential distribution. Assuming that the mean time of completing a customer service is 8 minutes, that is 8 minutes, we can estimate the probability that uh, 8 20 minutes, sorry, it is 20 minutes, we can estimate the probability that the customers for 1 hour you can accommodate 8 customers, probability that you can accommodate 8 customers per 1 hour. This can be per 1 hour. Okay, this can be calculated with the help of this the rate of time or mean time of the customer spending in the queue. So these there are several variety of applications of exponential distribution where which we come across in our real life. Okay, so time oriented probabilities, while calculating the time oriented probabilities, we apply exponential distribution to estimate the probabilities very accurately and with more precise and accuracy. Okay, so with this, I'd like to conclude my lecture by telling the facts that the density function of exponential distribution is lambda into e power minus lambda x, and the distributive function of the exponential distribution is 1 minus e power minus lambda x, and the mean of exponential distribution is 1 by lambda, and the variance is 1 by lambda square, and the skewness is 4, and the kurtosis is 5. Okay, and the MGF is lambda by lambda minus t, and the CGF is minus log of 1 minus t by lambda. So these are the things we have observed, and also we have seen the memoryless property, that is probability of x exceeding x plus 5 minutes, given that already x minutes are completed, will be automatically equal to the probability that x will exceed y minutes. That is the probability of a task will be completed uh, in at least x plus y minutes, given that already x minutes are completed. The probability will be automatically equal to the independent probability that the task will be completed in at least y minutes. So this is called the memoryless property. With this, advantages in an exponential distribution. We can calculate the time-oriented probabilities, and we can estimate, predict the things that are going to happen time to time in the future, in the forthcoming future, with more accuracy and high precision. Okay, so with this, I'd like to conclude my lecture, and in the next lecture, we'll meet with third module concept, that is decision theory. Thanks for your patience listening. Thank you all.
Like, share, and subscribe. Hit the bell icon for more updates.